Okay, this is the last part of lecture 16, talk about paratransport. Before we do that, let me give you the answer to the exercise, uh, break exercise. We were asked to show that for Christoffel symbols, which is has three indices, but it is symmetric respect to interchange of the two low indices. So, for example, here is low index new lambda. If you switch it, this you get the same Christoffel symbol back. You start from uh, the input of the covariant derivative of a scalar function is commutative. You can either differentiate back to uh, the new or uh, differentiate back to the new. For the scalar function, there's no difference between the covariant and ordinary derivatives. So therefore, I can replace the first covariant derivative by the uh, by the ordinary derivative. And now, uh, so now, but the secondary you cannot replace because this is now a tensor, no longer a scalar. I mean, the del nu phi is a tensor, so therefore you have to apply the formula for covariant derivative on on a covariant vector. So this one, both sides become this. Okay, it was this. Besides ordinary derivative, there's also Christoffel symbol term comes in. Okay, and of course, ordinary derivatives are commutative. It doesn't matter whether d mu d nu or d nu d mu. So these two terms cancel, and so therefore we're left with only the second term, which it shows clearly the coefficient uh, of Christoffel symbol are the same, which they here, which means they are interchange the positions of the low indices. Okay, so that's the proof. Now we'll talk about paratransport. Paratransport is a really fundamental concept in differential geometry. It will illuminate the meaning of covariant differentiation and associated Christoffel symbols. We can use this operation to clarify clearly see that geodesic is a straight positive curve uh, because it is a curve traced out by paratransports of tangent vectors, and also a paratransport of vector around a closed path will lead to the measure of the curvature of space, which we will use to derive Riemann curvature tensor this way. So now we're going to talk about the component change under differentiation. Okay, I would copy down these two equations we did before: the ordinary derivative, differential, two terms, and the uh, which also related to covariant differentiation and the Christoffel symbol. So, what is a paratransport? Why does one need to perform such an operation? Let's go back to see the definition of the root of a scalar function. Okay, del mu phi, which means differential phi is back to x mu. Now, which we know the definition is the scalar function evaluates x plus a little display in the neighborhood minus the phi of x divided by this h, where the h equal to 0. That's the definition of the derivative. Now, the numerator involves function's value at two different locations. That's the key difference. To take a derivative, you must necessarily involve evaluate the function at two different locations. So now evaluate a quarterly independent scalar function at two locations. Does not pose any complication. You just because the coordinate doesn't change. But that's not the case for vector components because differential dA mu vector will involve the difference of of a value x plus dx and of f of x. Let me call the first one is the value of the components at location 2 compare with the value of the component at location 1. Okay. Now, again, remember that the component of a vector is projection of the vector onto the basis. So the evaluation at two different locations, uh, they are separate by dx, will have, there are two sources of the difference change vectors. It was the one possible, the vector itself changes. All right, the vector at 2 is different from vector 1. That's the, but also, even without talking about the vector itself changing, the coordinate have changed because component made two components, two parts, the vector itself and the and the basis. So therefore, the total change, the differential, has two parts. One I call the true part, and one I call the coordinate part. The vector itself can change. We call that true change. Okay, is equal to the first term here, e dot dA, change of vector. And in fact, we'll identify that with the covariant differentiation. The other term is projection of A onto the change in the base itself. So this change is the product of the component of the vector A and the separation dx. In other words, if I say, well, what will be the guess the coordinate change? The coordinate change would be proportional to separation. Clearly, there's no separation. There's no, and also would expect it to be proportional to A itself. Then coefficient is we identify with Christoffel symbol. Okay, this is the second term, A dot DE. Okay, so the first term we're associated with the true change. The second term is coordinate change. Okay, and this shows the true change covariant derivative. The second term is related to Christoffel symbol. So parallel transport is the process of moving a tensor without changing the tensor itself. Okay, the only change in tensor components under a parallel transport is due to the coordinate changes. So it was the total change, just the coordinate. There's no true change because that's what we call it parallel. In the flat space with Cartesian coordinate, this is trivial. There's no coordinate change from part, so therefore dA equal to 0. Okay. But in a flat space with a curvilinear coordinate, for example, the polar coordinates, this parallel transport itself induces component changes, even though the vector itself doesn't change. Okay. This a little more detail. Suppose I have a flat plane. I have a vector at A, a parallel transport vector located at 2. Okay. And now I'm in the polar coordinates. At position A, the radial component, let's say the vector origin in the radial component, and the perpendicular orthogonal direction is the angular direction, okay, E5. But at location 2, now even though the vector A is original parallel to the radial vector in the position A, but it's no longer parallel to the radial direction in the point 2. Okay, so therefore, at position 1, the vector has components a sub phi, which is 0 because there's no component in the angular direction, and then there's the component in the radial direction. Since that's all there is, that's equal to the radial direction equal to the magnitude of A. At position 2, these components both are non-zero, and their square and square root is the length. Okay. So the difference came about because the basis at position A is different from basis at position 2. So therefore, in the vector example discussed here, we were talking about the true change is equal to 0 under parallel transport. Yeah. So therefore, the mathematical expression of a parallel transport of vector component is the differential plus the Gustavo symbol, basically, uh, is equal to 0. So it was the total change is equal to the uh, coordinate change only. Remember we said that the metric tensor G mu nu is covariantly constant, meaning you take a covariant derivative, the metric equals 0. Now we can understand this covariant constancy of a tensor means that any change of tensor component due to coordinate change only. Okay, remember we said parallel transport means when component change is due to entirely to coordinate change, not to vector itself, the tensor itself. But the change of metric, by definition, is pure coordinate change because metric is nothing but just basis vectors. 0. Now, once we have this understand what it is a parallel transport, now we can view the geodesic as the straight line. Okay, remember we talked about in chapter just give some idea that first of all we derived the geodesic equation through the requirement it has the extreme length. Then we also in the box discussion we started but not completed discussion geodesic straight line. Now we can see in much simpler way to see it that geodesic is a straight line. So remember we say a curve is a vector component depends on curve parameter, and so we're not talking about parallel transport a vector along a curve can be written as this way, just the change in curve parameter as covariant difference is equal to 0. So the differential of the A is respect to ordinate differential is respect to the curve parameter plus this Gustavo symbol term, which is due to the coordinate change only. Now we can view the geodesic as a straight line as the line constructed by parallel transport as tangent vectors. Okay, it was A here is replaced by the tangent dx this okay. And you say, well, why is this a definition of straight line? Well, you take the ordinary flat space we're familiar with. We have a line. If it's tangent, if a parallel transport a tangent, you trace out a straight line. So that's the one way you can understand the straight line as a parallel transport of a tangent vector. Now we plug in the expression for into here, dx d sigma into this equation. So the first term becomes the second derivative. The second just replace a by dx d sigma again. But you don't recognize that's precisely the geodetic equation we derived in chapter 5. Okay, so so that's another view of geodesic as a straight line, and using parallel transport you can immediately derive it. One that's related exercise I like to do in 11.2. When a vector is parallel transport along a geodesic, the angle between the vector and the line, which the tangent is unchanged. Okay, when you parallel transport, this angle remains the same, which we'll use as when we talk about parallel transport vector on a closed path. Okay, takeaway from this lecture 16. We talk about general coordinate transformations, and in particular for general tensor, we say here I illustrate with one contravariant index and one covariant index. Then for each index, I have a transformation matrix. For the contravariant index, I have dx prime dx, and for covariant, I have dx dx prime. Okay, and so anyway, the transformation can be written as partial derivatives. And we say the ordinary derivative is not a tensor So therefore, we're looking for a derivative that's a tensor we call covariant derivative. Okay. Now, the tensor components is projection of A along the basis. So therefore, ordinary derivative means you're holding the base vector differential respect to the vector itself, and then holding the vector itself differential respect to the basis. Now, the first one corresponds to the change in the vector itself. We call true change. That's only when the vector really changes. And the second one is simply due to the coordinate change, okay, because the bases are moved from going. And for this, we parameterize, like, basically we parameterize the derivative of the basis as the Christoffel symbol. So parallel transport of vector simply means the covariant derivative of the vector is unchanged. Means the change due to entirely due to coordinate change. And the geodesic can be thought, as we just said, is equal to parallel transport of a tangent vector along a curve. That curve traced out by a tangent, parallel transport of tangent is the geodesic equation. And also, differentiation of the metric is but also we give a number argument why these are reasonable results. Okay, so that's to be expected. But anyway, using this result, we can also uh, write it out into a Christoffel symbol and use 6 permutation, and we can end up showing that the uh, Christoffel symbol is directly related to the first derivative of the metric. So the other part of chapter 11, in lecture 17, we finally talk about Riemann curvature tensor, derive it, and then we talk about principle of general covariance, even though we've been using the principle of general covariance all along, but here we have all the proper math context to state exactly what it is. And also it gives a way for cases how to go from special relativity to general relativity. And then finally to Einstein field equation. Okay, the way we'll be following with uh, uh, knowing the curvature, Riemann curvature tensor and how to get Einstein tensor. That's one way. Another way is just using the principle of least action, which is a little bit more advanced topic. But you see, it's not that hard to understand either.